That purpose is very simple to observe the motion of object that is moving at the constant speed, which is uniform motion. So here is what uniform motion is. It's based on the momentum principle. What aka Newton's second law, what it tells us is force is proportional to the change of momentum, because by definition, momentum is equal to mass times velocity. It implies you have zero force, that there's no change in velocity. So eventually you will get to uniform motion. Experiment. That's how I made this experiment, how I did it. Result, precision, very small, which means it was great. And percent error means you have I had high accuracy on this experiment. And physics principle, uh, a little bit details of computational model. It's based on, of course, it's based on Newton's second law, but since we have no force, it goes with first law, which means constant velocity. And because we know we will have constant velocity, we can we can apply position update equation to the code and the theoretical measurement. Systems and surroundings. The yellow ball represents where I'm gonna start to move my object. Green path is where the green bar is my path, and blue shows my car. I'm gonna exalt my force. Those three are in my system, and all the other objects are surroundings. In the real world, there will be distinction between the real world and my experiment. There will be some interactions between the object and air, which is drag force, or my object and ground, which is frictional forces. That can make my car go slower. Procedure is pretty simple. Flat surface, the table, and consistent force at the beginning, consistent distance, consistent length of time. Initial condition, the velocity should have been 0.5 meters per second, and position 0, of course, and net force, the vector addition of all the forces should be 0. Here's the observation. As you can see, the result was very good because it looks like literally a line. And we expect the experiment was expected to uniform motion. Here, A represents the slope, which is velocity. We are interested in it, which is 0.49. So it was, I can say it was satisfying. Similar stuff goes with trial number 2 and number 3. So let me go faster. In code, visualization, how we do was given, and initial condition, again, position 0 and velocity 0.5 meters per second. Here I applied the formula, the distance, the change in velocity and change in distance formula based on momentum principle. Here is the code execution. Constant velocity, uniform motion, perfect. Similarities and differences. Those two, my experiment and theoretical, the visualized interpretation of my code was very similar. There were no such difference that I have to emphasize. There were a slight amount of error that causes my experimenter results to be a little bit lower than what we expect, the theoretical value, because that's probably because of the frictional forces in the real world, given by normal force times frictional constant. What if? How your results will change if you flip the axis? Because we are dealing with vectors, and vector has magnitude and direction. That's what vector is, vector quantity. if we flip it, the positive will be negative and negative will be positive. So we will just get all the same values with negative value. The next discussion, what does that mean? Is it possible for you to say how many pushes and pulls are added together to give zero net force? Answer is no, because what we see in the real world is resultant vector, which is just the result of a whole bunch of potential vectors out there. So you cannot guarantee it how many vectors were added to.